I'm very happy to be presenting today's speakers. The first speaker today is Professor Maria Esteban from the University of Paris-Dauphine and CNRS France. Professor Esteban was born in the Basque Country of Spain and moved to Paris for her graduate studies, where she did all of her career. Professor Esteban also spent some of her early years in Brazil, so she knows well the host country. Professor Esteban is deeply involved and dedicated to promotion of and development of mathematics in Europe. She is a honorary member of the London and Royal Spanish Mathematical Society. She holds honorary degree of a few European universities. She is a president and member of scientific boards of, I would say, countless European mathematical societies, institutions, research institutes, and even cities. She is a holder of the Knight of the Merit National Order of Paris for her services to mathematics and development of mathematics in Europe and France. The research career of Professor Esteban started in Paris 6, the Université de Pierre and Marie Curie, where she did her PhD and later her doctorat d'état, working with Professors Brizis and Pierre-Louis Lyons. And she's worked in Paris and has established herself as a leading expert in nonlinear elliptic partial differential equations and calculus of variations and their applications to mathematical physics. So today she will speak about symmetry and symmetry breaking in the field of elliptic PDEs. Professor Esteban, you have the floor. Thank you.
Thank you very much, Boyan, for this nice introduction. And I would like to start by thanking the program committee for the invitation to speak here. I'm really very pleased and very honored to give this lecture in this ICM. I also want to thank the local organizers for the great job they are doing. Okay, so I'm going to speak about symmetry, symmetry breaking, rigidity, and flows in elliptic PDEs. And practically everything I'm going to say has been done in collaboration with Jean Dolbeau from my university in Paris-Dauphine and Michael Loss from Georgia Tech University in Atlanta. And they would deserve to be here giving this lecture as much as me. So the outline of the talk is, first I will say some words about symmetry and symmetry breaking in PDEs and elsewhere. Then I will speak a little bit about functional inequalities in general. Then I will explain a little bit how to use linear and nonlinear flows to prove linear functional inequalities and describe how the optimizers of these functional inequalities are and base constants and things like that. And then I will say some words about how these results have as corollaries the obtention of some very interesting spectral estimates for Schrödinger operators in compact and non-compact manifolds. Okay, so I start with symmetry and symmetry breaking. I will not say anything deep, just some words about it. So the issue of symmetry and symmetry breaking is really fundamental in all areas of science. Symmetry is often assimilated to order and beauty, and I think that in mathematics we see symmetry as a very positive property, and maybe we see symmetry breaking as disorder. So symmetries are fundamental properties of laws of physics. They impose constraints on modeling phenomena, and I would say that they serve really as criteria of classification in many systems. And probably the first scientist who spoke about symmetry in a precise and scientific way was Pierre Curie when he was working on crystallography. He announced what is called the Curie's principle of symmetry, which actually was a little bit wrong, because Curie thought that when a system has all the how to say, the constraints, etc., to allow for symmetric solutions, the solution should be symmetric. So he announced such a principle, a vague principle, and he himself, some years later, understood that there were cases in which the principle was not valid, that you can have really a system which is invariant by the action of some symmetry group, but still you can have solutions that are not symmetric. Symmetry breaking is a source of many interesting phenomena. And I think at the level of science in general, probably when you talk to physicists, chemists, etc., very often they are more interested about symmetry breaking than about symmetry, because symmetry breaking gives rise to very interesting phenomena. For example, phase transitions and complex dynamics, instability, segregation and self-organization, etc. So actually, both phenomena are interesting, but probably symmetry breaking globally in science is in some sense more interesting. So knowing a priori the symmetry properties of solutions of PDEs and of variational problems, which are invariant under the action from symmetry group, is of fundamental importance. Of course, it's important by itself. When we prove as mathematicians the existence of solutions of some problem, we are often very interested about the qualitative properties of the solutions. So, for example, symmetry. But it is also very useful from the practical point of view. If, for example, you have a very complex problem in an applied field, let's say, for example, in physics, and you want to simulate the solutions because you can't solve the problem explicitly, and you want to use the computer in a simulation to find approximate solutions, it is very important to know the symmetry properties that you can expect, because the more symmetries you have, the fewer degrees of freedom, and so the simpler the numerical computation. So really, knowing symmetry properties a priori is very important in simulations, numerical simulations, especially in the case of complex problems. Okay, so now let me say some words about the key word of my talk, which is functional inequalities. Functional inequalities in a vague way are expressions like this. So you have an inequality. You have here a functional which depends on some function v, some derivatives, maybe x, which is the space. Okay, so, and then you want to see if this quantity is going to be bounded by another quantity in which, in general, you have more derivatives. Okay? And then you are interested in knowing if such an inequality is possible, what would be the smallest constant that you can put there. Okay? You are working in some given space. So this is very vague, but we will see some inequalities later. So functional inequalities play a very important role in analysis, in geometry also. The traditional role of functional inequalities was to obtain a priori estimates for solution of PDEs and variational problems. And those a priori estimates very often are essential to prove existence results. These kind of inequalities also have been very much used to analyze the long-time behavior of solutions of evolution problems. You have some, for example, heat equation or wave equation, and in order to understand, for example, the decay properties of the solutions, you use this kind of inequalities. And recently, these kind of inequalities have played a very important role in the description of the precise blow-up profile for finite time blow-up phenomena. There's been a lot of activity in the last 10, 50 years understanding the blow-up, finite time blow-up for nonlinear evolution equations like nonlinear Schrödinger equation, nonlinear heat equation. And when you try to describe exactly the geometry of the blow-up, these kind of inequalities play a very important role. So there are many examples of inequalities, or people here who work in analysis know many of them. I just put some names here. There are many more, but there are some, they are very, very classical, like Hardy, Helde, Poincaré inequalities, etc. Some are more recent, like Locke, Sobolev, Caffarelli, Nirenberg inequalities, etc. But there's a huge quantity of inequalities in analysis And I would say that these inequalities, I had a colleague at some point, a very well-known colleague in Dauphine, who used to say that inequalities was not really a very interesting thing, that real mathematicians prove equalities and not inequalities. I totally disagree with him. I think that really the big set of inequalities that we have in analysis are really a very important toolbox in analysis and geometry. They are very, very useful. Okay, so when you have such an inequality, there are questions that you ask yourself immediately. If you have a best constant in the inequality, is the best constant achieved or not? If it's achieved, what is its value? And also, if it's achieved and you have extremal functions, functions for which you have equality, then how do they look like? For example, can you say something about symmetry or the qualitative properties? Okay, now let's come to the last keyword of my talk, which is flows. So in the last, let's say, 20 years, flows, linear and nonlinear flows, and entropy production methods have been used to prove many, or to study many kinds of inequalities. For example, in the case of Sobolev, Log-Sobolev, Galgardo-Nirenberg, Hardy-Sobolev inequalities, they have used for the things like, for example, in optimal transport theory, etc. So it's an area of analysis that has developed very much in the last decades. In most cases, when you use flow, linear and nonlinear flow methods to prove inequalities, not only you are able to prove the inequalities, but you are able also to get the best constants and also some information about the properties of the extremal functions. So they are really, these flow methods, we are going to see afterwards how they work, they are really very powerful to give us information about functional inequalities. Okay, and I would just like to add that it's not only in analysis that the flows have played a very important role in the recent decades, but for example, in geometry also, we all know the many important results obtained with, for example, Yamabe flow or Ricci flow. Okay, so now I'm going to present to you two types of inequalities in which flow methods have been a very important tool to prove, to say many things, probably to prove optimal results about this inequality. So I will start with a very simple-looking inequality. It's a Sobolev-like inequality in a sphere, so we are in the sphere of dimension dsd. And this inequality tells you it's like a Sobolev inequality in some sense. This inequality tells you that the H1 norm of a function in the sphere bounds the LP norm for P between 2 and 2 star, which is the critical Sobolev exponent, which is 2d over d minus 2 if dimension is larger than 3. Okay, so this inequality is very well known, and it was very well known for many years. But what has been more recent is the fact that this constant here is the best constant that you can achieve, and the fact that the optimizes, so when you have equality, the only possible solutions are the constant functions. Of course, in a sphere, since a sphere is a compact manifold, the constants are in the H1, in the Sobolev space. Okay. So let me just make a little remark, is that in the extremal case when P is equal to 2 star, this inequality you can see by using a projection, stereographic projection on the plane, on the space, sorry, that these inequalities are equivalent to the classical Sobolev, critical Sobolev inequalities. Okay, so as I said, these kind of inequalities were very well known for many years, but what has been more recent is the proof of the best constant and the fact that the optimizers were only constant functions. This is a rigidity result, okay? So the first time that this was proved by Bidot, Véron, and Véron in a paper that was published in Invenciones in '91, and they used PDE methods, rigidity methods, to prove this result. And 2 years later, there was a paper published also in Invenciones by Bill Beckner, who using a different method, completely different method, using harmonic analysis methods, proved the same result. By the unfairness of our business, These inequalities are known as Beckner Inequalities, even if the first proof was not by him. Anyway, so these inequalities in the 90s were really, many people were interested about them and about how to prove them with different methods, etc. And to show that, I will speak of a third proof that appeared in 96. And in this case, it was, this proof was made by two probabilists in Toulouse, Bacri and Ledoux, using ideas coming from what is called the Bacri-Emery method of Carré-Duchamp, which is very well known in probability theory. And what Bacri-Ledoux did was to prove the same result. So this is the best constant, and the only optimizers are the constant functions, but they did it only for p's that are between 2 and 2 sharp. And 2 sharp is this number, and you can see that for every dimension, this number is strictly less than 2 star. So what they published in this paper was something that was already known and even weaker than the previous results, because they were not able to cover the whole interval p between 2 and 2 star. So the method stopped before 2 star. But despite the fact that this result is weaker than the other ones, this is the one that I am going to present to you, because I think the method is, in fact, very interesting. And it has really been used hundreds of times to prove other things. So I think that the method, even if the result was not optimal, but the method is really very interesting. And I am going to explain to you the idea is very, very simple. So this is an inequality they wanted to study, Bacri and Ledoux. So what they do first is, instead of working with the function u, they work with the function rho, which is u to the p. Okay? So you write this inequality for rho instead of for u. You get this inequality here. And so what they wanted to prove or to study is the inequality I larger than d times e, when I is this integral, this kinetic energy on the left-hand side, and e is this here divided by p minus 2. Okay? So they want to prove this inequality, I larger than dE. And these names are not by chance. There is a link here that I can describe with information theory. And so E is for entropy and I is for Fisher information. There is an important link with information theory in all this business. Okay, so they wanted to prove that or to study that. So the idea they had is the following. They want to use a flow method. So they look at the linear heat equation. So this is the heat equation on the sphere. So this Laplacian is the Laplace-Beltrami operator on the sphere ST. And they want to solve it with a given initium datum, rho 0. Okay? And what they proved, and it's very easy to do it formally, you can do it in a little piece of paper. Formally, it's very easy. Rigorously, you have to work a little bit more. What they saw is that you use the linear heat equation, then along this flow, the mass of rho on the sphere is invariant along the flow, so the mass is invariant. And then when p is less than 2 sharp, this number I gave you before, when p is less than 2 sharp, then they could prove that the derivative of the entropy is equal to minus the information, and that the derivative of the information is less than minus d times the information. Okay? But these inequalities are true only if 2 is less than 2 sharp. Doesn't work. Okay. Okay, so what they want to prove is that I is larger than d times 0. So they want to prove that this combination here is non-negative for every function. So if I recap what I said in the previous slide, what they saw is that for p less than 2 sharp, the derivative of this guy along the nonlinear, about the linear heat equation, about this flow, is less than 0. On the other hand, it's not difficult to see that if you take a reasonable initial datum, then the solution of the heat equation, linear heat equation, converges to a constant as t goes to infinity, and the limit of this quantity is 0. So you see that if you have a decaying quantity that converges to 0, at all finite time is non-negative. So if you started at a given rho 0, this quantity will be always positive or 0. It can't be negative, because if it's negative, it can't decay towards 0. Okay? So you see the idea of the proof is very, very simple. Now, for several years, I talked with Beckner several times about this, and he was very confused, because they said, well, I mean, we know that the result is 2 for P between 2 and 2 star, and we are unable to make this method work in that case, and they didn't know what was happening. They didn't know why the method, which was so simple, was not optimal. And in 2017, with Dolbeau and Loss, we have explained, and dedicated to Beckner in a volume dedicated to his 60 years, we have explained why the method couldn't work. Actually, we have seen that for P between 2 sharp and 2 star, even if the inequality is 2, the method can't work, because we found an explicit function rho 0, explicit, so that when you look at the linear heat equation and you take as initial datum this specific function that we found, you can see that when you differentiate this quantity at time t equal to 0, you find a positive value. So it's not decaying. So when you go through 2 sharp, the method can't work. There is no way. It's not that they were missing something. It is that it's impossible. This quantity is not decaying as it was decaying in the case when P was less than 2 sharp. So we explained why the Beckner-Ledoux method couldn't work in that case, and at the same time we gave an alternative. We proposed to use a nonlinear heat equation, so d rho dt equal to Laplacian rho m. You have to choose the m well, you have to choose it. It's not any m. M is different from 1. And actually, m is less than 1. So this is not a porous medio equation. This is a fast diffusion equation, which is quite singular. But in any case, we can use the idea of Beckner-Emery, Beckner-Ledoux, and try to do the same thing. So what we did with this nonlinear flow now is to prove that for every P between 2 and 2 stars, so in the optimal range, this nonlinear flow allows us to see that the information, that this quantity is decaying along the nonlinear flow. So we extended the idea they had, but in order to do that, we had to use nonlinear flows. Actually, we did more than that. We saw that by using this flow, we can even treat cases where P is less than 2, which was something that was not very well understood before. So we saw that this nonlinear flow, the linear flow method of Beckner-Emery and Ledoux is very powerful, very nice, but we saw that in order to deal with some inequalities, you need to go to nonlinear flows, okay? And it worked very fine here. And so this is what we did in 2017. And then at the same time, the last maybe 10 years, we have been working with Dolbeau, Loss, and other collaborators about a family of inequalities that is called Caffarelli-Kohn-Nirenberg inequalities. They were introduced in the 80s by Caffarelli-Kohn-Nirenberg in a paper in which they were dealing with studying the regularity of Navier-Stokes equations. So they introduced these inequalities, which, as you see, is inequalities of the same kind like Sobolev inequalities, but the difference is that you have weights. And so what they proved in the paper, initial paper, Caffarelli-Kohn-Nirenberg in '84, is that these inequalities are true when B, which is the parameter which is here in the denominator, is between A and A plus 1, A being the parameter which is in the other denominator. And they also show that in order to have these inequalities true, in order to have the scale invariance actually, you see that actually there is a relation between the 3 parameters in the inequalities. So here you have the parameter P, the parameter B, and the parameter A. They are not all free. In order to have the scale invariance, you have a relation between the 3 of them, which can be written, for example, like this. So you fix A and B, and this is the dimension, then P is given by this formula. So you have only 2 free parameters in these inequalities. Okay, so let me just make a little comment. So we see that these inequalities cannot be only true for B between A and A plus 1. And so if you look at the case at the left-hand side, when B goes to A, then P goes to 2D over D minus 2. So these inequalities go towards the Sobolev inequality. And if you take the other limit, you take b going to a plus 1, then p goes to 2. So the inequalities go towards Hardy inequalities. So these inequalities are just interpolation inequalities between Hardy and Sobolev inequalities. Okay, let me make a little remark about the fact that if I call CAB the best constant in this inequality, that we know it's existent by the work of Caffarelli-Nirenberg, being the best constant in this inequality is equivalent to this minimization problem. Then 1 over the constant is the infimum of a functional, which is this quotient here, where you put in the numerator, you put the right-hand side here, and in the denominator, you put the left-hand side. Okay? And I write it because in some of my comments, sometimes I will speak about extremal functions, sometimes I will speak about minimizers. It's the same. The extremal functions here are the minimizers in this minimization problem. Okay, so these inequalities, you see, they are totally compatible with rotations, because the space RD is invariant by rotation, of course. The gradient operator also, the weights are invariant by rotation, so everything is invariant by rotation. So if we apply the naive Curie's principle here, we would think that the extremal functions had a very good chance of being also radially symmetric. And I remember when I started working in research in the 80s, and I already studied some problems of symmetry and symmetry breaking for other problems. In the math community, in the PD community, there was the belief, naive belief, that what you should expect in cases of invariance by rotation group, for example, is that the minimizers of the minimization problem should have the symmetry of the problem. But since the 80s, we have learned that there are many, many cases in which this is not the case. So here, in any case, well, there is a chance that the extremals are radially symmetric, but just in case, let me define, so if the best constant here is called CAB, let me call C star AB the best constant when we are looking only at functions V which are radially symmetric. And by definition, it's very easy to see that you have this inequality. And in the radial case, you know everything. You know the value of the constant C star, because you are lucky when you look at the Euler-Lagrange equations on this inequality, and you are in the radial case, you have an ODE, a nonlinear ODE, that you are able to solve explicitly by using special functions. Okay? So you know exactly the minimizers, or the extremal functions, the radial ones, and they look like this. So up to a scalar multiplication and dilation, the optimal radial function in this inequality is given by this expression. So we know everything in the radial case. And so the question is it the case that these functions are the global minimizers, the global extremals, or not? Okay, so that was the question that we started to look at several years ago. So many people have worked in these kind of problems. I haven't listed everybody. There are many, many results. I have listed just some people who are really contributed in an important way. So the result of all these works and more is that when you look at this is the set B between A and A plus 1. So this strip is the strip in which you are studying your inequalities. Okay, so the result of all these works is that you are in the case when A is positive, so this part here. There were many people who looked at this. For example, the case A equal to B equal to 0, so this point here, was studied, by instance, by Aubin and Talenti, and it corresponds to the critical Sobolev inequality. If you look at this segment here, which is A equal to 0, B between 0 and 1, this was extensively studied by Elliott-Leaf. And then the general case, A positive, etc., here was studied by Chuchu and Pierre-Louis Lyon, Soriuchi. Many people have contributed to that. And what people proved is that there were extremal functions and that they were radially symmetric. So there was symmetry in this case, and the methods to prove symmetry were either symmetrization techniques or moving planes, or this kind of the usual methods to prove symmetry of positive solutions of nonlinear PDE. Okay, so then in the case A negative, the situation becomes more complicated because when A is negative in the corresponding equations, you can't use moving planes. It's not compatible with the moving planes method, and the usual symmetrization techniques don't work either. So the case A negative is complicated, and there is only, there were some little partial results by Lin 1 and by Dolbeau, Tarantello, and myself in dimension 2, in which we proved some very, very partial results of symmetry in the case when A was positive. And there was a very nice result later by Beta, Brock, Mercaldo, and Posteraro, where they used a very sophisticated symmetrization method to prove that in this triangle, when A is negative but B is positive, still you can prove that the minimizers of the inequalities, the extremal functions, are radially symmetric. Okay. But in 2001, there was a paper by Katrina Wang where they had the idea to do the following. They said, well, we have our radial minimizers, okay? We want to see if they are global minimizers or not. Let's look at the linear stability around them. Okay, so what they did is to look at this functional, and they looked at the linear stability. They looked at the Hessian around the radial minimizers when you look in the whole space of functions. Okay, and what they noticed, they could compute, not completely, they couldn't compute the whole computation. They didn't finish the computation in this paper, but then Feli-Snyder 2 years later, they computed it. And what they proved is that there is this red zone, this red region here, where what happens is that the radial minimizers are not local minimizers in the set of all functions. They are saddle points. And if they are saddle points, they are unstable, and of course they can't be global minimizers. Okay? So in those cases, you are sure you have symmetry breaking. So this is this red region, which is explicitly described in the paper by Feli-Snyder. So this region is, the limit of it is a curve which is explicit. It's a complicated proof. It's really a very technical result, but they proved that. And then once they proved that, of course, the question is, and what happens in this white region? What happens when you can't use symmetrization techniques or moving planes? But you know, because in this white region, it is well known that the radial minimizer is stable, is linear stable, is a local minimum in the full set of functions. So you are a local minimum, you have a chance of being a global minimum, okay? So the conjecture was that in this white region, whenever the radial solution is stable, then is the global minimizer, okay? So that was the conjecture. But, well, you never know. You can have surprises. And for example, we have a surprise in 2011, just for fun. We were just playing a little bit with the methods we were using to try to see if we could export the methods and the ideas we were having to more complicated inequalities. And just for fun, we were not even thinking of writing a paper. With Dolbeau, we started to look at this problem. This is an inequality that was also is Caffarelli-Nirenberg inequalities that were actually in the initial paper of Caffarelli-Nirenberg. So you look at them, they look at the previous one, but you have a further interpolation here. You see, instead of having only this integral here, you have the interpolation with the parameter theta of this term and this term. Okay, so it's a family, it's a large family, larger family of inequalities, and in the case theta equal to 1, we are in the previous case. And the radial case for these inequalities, which are very complex, was, with a lot of patience and work, was studied by Del Pino, Dolbeau, Filipas, and Terticas. And in the radial case, they know everything. They know the value of the base constant. You see, it's a horrible thing. Well, they use special functions to compute all that. But the bad surprise we had, it was in 2011, we discovered with Dolbeau, Tarantello, and Terticas that there were cases for these inequalities, in cases when theta was small, we discovered that there were cases of symmetry breaking in cases where the radial solution was stable. So the radial solution was stable, it was a local minimum, but it was not the global minimum, there was symmetry breaking. And for us, this was very, in 2011, we were not sure about the conjecture anymore, because we thought here is a case in which linear stability doesn't guarantee symmetry, okay? But we made a lot of numerical computations for this problem, and we saw that every time that we found this strange phenomenon that we had the stability of the radial minimizer, but still it was not the global minimum, it always happened for values of theta which were small enough. We never could manage to find any example when theta was going towards 1, which was our initial aim, to look at the case theta equal to 1. So this result made us feel a little bit not very comfortable with the conjecture, but at the same time, we didn't find any counterexamples. So we were a little bit, we didn't know what to expect. We continued to work to try to prove that conjecture, and after several intermediate works that I am not going to describe, in 2016, we were able to prove the conjecture in the case theta equal to 1. So what we have proved is that for theta equal to 1, so when you have only this term disappears here, so in the initial class of inequalities, whenever the radial minimizer is stable, it is the global minimizer. So the only way to break the symmetry is to have instability of the radial extremal. And this is very interesting to understand because when you are looking at a real problem, for example, real model in physics, etc., you want to understand what can be the source of symmetry breaking. So it's very interesting to try to understand in which cases you can expect symmetry breaking or not, and what are the things that trigger the symmetry breaking. Okay. So, okay. So this is the theorem that we have proved in 2016. We have proved that in the stability region for the radial extremals, if D is larger than or equal to 2, the optimality is achieved by radial functions. So we have these graphics, you see? Either we have instability in the red zone, or we have green, so symmetry everywhere. So the conjecture is true. Okay, so I'm trying to tell you in the remaining time how we prove this. I don't have much time, I was a little bit slow. So our idea was to, well, the first idea, we tried many things, but finally what worked was the following. We made a very simple change of variables, which is just stretching R to R alpha. We didn't touch the angular variables, so for a function W, we depends on R and W, we define V like this. We define some numbers like this. Well, it's not, don't look at the details. The important thing is that this Caffarelli-Nirenberg inequality for V, when we write it for W, so when we stretch in the radial direction, then we find an inequality which is very funny. If you look at this inequality here now, you see that the measure we have here is the Lebesgue measure in dimension n. Here we have some kind of gradient square. It's not exactly a gradient because you see in polar coordinates, the angular part is the same, but the radial derivative is multiplied by some number alpha, the alpha which was in the stretching here, but still it's like a gradient. We have the Lebesgue measure in dimension n, and which is very nice, is that here we have the 2n over n minus 2 power of W. So this inequality looks like critical Sobolev inequality in dimension n. And when we saw that, we saw, maybe we have a way of dealing with this. The problem is that I am telling you things that are totally not very correct. I'm telling you that, that this looks like Sobolev inequality in dimension n, and it is true in terms of scaling. But you look at the details, it's not at all the case. First, n is not a dimension. N is a number which is given as a function of b, p, n, alpha, etc., and there is no reason why n should be an integer. So when I speak of dimension n, I am a little bit light. You know, it could be a non-integer. Second thing, this is the Lebesgue measure in dimension n, even if n is an integer, but the problem is that we are integrating in Rd. So there is a discrepancy between the dimension in which we integrate and the dimension between quotes of the Lebesgue measure we are looking at. Okay, so, but still, we thought that maybe, since the scaling properties of this inequality is like the Sobolev inequality, maybe we could try to use a flow method that can work for Sobolev inequality. So we tried to do that, and we just noticed that in this new setting, the stability region is given by alpha, this number who is here in the stretching, alpha less than alpha fs, which is a given explicit number. Okay, so now what we did was to use the same idea we had used in the other problem in the sphere. So this idea of Bacry-Ledoux, Emery. So what we do again is, instead of working with W, we're working with U, which is the P power of W. And then the inequality we want to prove or study is the integral of U with this Lebesgue measure in dimension n is bounded by a constant times I of U. I is again for information. So I is given like this, can be written like this. You want to read the integral of U, derivative of P squared, etc. And P is a power of U. I mean, this is things that, I mean, you can write like things or not, but that's what we decided. And in terms of information theory, this guy here is the Fisher information, and this guy here is called the pressure function. Okay, but this is totally equivalent to the Sobolev inequalities. Now, we want to prove that. What is the strategy? We said, well, okay, we know how to use flows to prove, to study a certain number of inequalities. Try to do it here. The question is, you have to find the flow. So the idea is that we want to find a flow such that in the stability region, we are able to prove that the mass of the function is stable, is constant, and that the information theory, this functional that appears here, is decreasing. So we want to follow the strategy we followed in the case of the sphere, in the first example I talked to you about. Okay? So we tried to mimic that. Of course, we knew it would be much more difficult, but we tried to do that, and to see also that even if this function is decreasing, the equality case would mean that we would have radially symmetric functions. So our aim is to do that. So we did it, I mean, we tried. So the flow we used is a flow that was mimicking exactly what we did in the sphere, that result we proved in the Bacry case. So what we do is to take an elliptic equation, which is like this, du dt L um. L is the elliptic operator, is like the Laplacian associated with the pseudo-derivative d. So in polar coordinates, it's like a Laplacian, but only the terms that are radial derivatives are multiplied by alpha squared, but it's like a Laplacian in some sense. And for m, we choose 1 minus 1 over n. So this is less than 1. And so this is a fast diffusion equation. We don't know if this equation is well posed for reasonable initial data, but as well we try to work with it. Okay, so what we proved, we tried to prove these decaying properties. What we proved is the following thing. We looked at the derivative of the information, and we saw, after a lot of computations, that this derivative is equal to minus a positive constant times some integral. And if we want to see that this I is a Lyapunov function, is a decaying function, clearly, since we have a minus here, what we need to prove is that this integral is positive. Okay, so this integral, we wrote it in the following way. We wrote it as kappa of p, p to some power, and this is the Lebesgue measure in dimension n. And then we wanted to prove that this guy is positive. So when you want, there was a talk yesterday or the day before, when you want to prove that a function is positive, it's very difficult unless you see that this is a sum of squares. Okay, so we try to see the expression of this kappa of p is very long. It's almost 1 page of terms. But then we try to put them together to see if we could find squares there. And indeed, we found that this kappa p that appears here in the integrand is a first square of a complicated expression, plus a second square. We were very, very optimistic at that point. And then we found the remaining terms. And the remaining terms looked like an awful expression. But if you know some differential geometry, you see that here you have a chance of looking at the sign of this horrible expression by using the Bochner-Lisnerovich-Weitzenbock formula that relates Ricci curvature with the Hessian, etc. And so by using this Bochner-Weitzenbock-Lisnerovich formula, we show that we had a square plus something here that is bounded below by a constant times the angular gradient of p to the square plus another constant, the fourth power of this. So we see immediately that if alpha is less than alpha fs, and I told you before that that was the zone in which we had the stability of the radial minimizer, exactly the stability zone corresponds to the case when this thing is positive, then we see that this guy is going to be positive. So finally, what we have seen is that in the stability region, our information function is decaying. So we can mimic again the ideas of Bacry, Ledoux, and Emery, because we have found a flow for which our functional is decaying. And it will allow us to prove also that when you decay towards the limit, you can identify your functions. And what happens, I don't have much time, so I'm going to just pass through. So what happens in the end is you have something like that. You have you have an elliptic proof. You are in the stability zone. You take critical points U0, P0 of the Euler-Lagrange equations, and then what you do is you differentiate at time equal to 0 the information functional. Then by the chain rule you can write it like this, but then at initial time ut is equal to U0. Okay, so you can write this like this, but U0 was a critical point, so this guy is equal to 0. But now we know that this guy, by the previous computations, is equal to this expression that is bounded below by these guys. And now I know that for my critical point, this kappa 0 is 0, but is bounded below by a square plus this quantity plus this quantity. And then, if alpha is less than alpha fs, which is the zone of stability, everybody here is positive. So if I have a sum of positive terms that is less than or equal to 0, necessarily each of them has to be equal to 0. But if every term is equal to 0, what happens? Let's look at this one, for example. I have positive constants here, I have an integral of something is equal to 0 in the stability zone. Then the integral has to be equal to 0 almost everywhere. But when I look at what I have here, I have the angular derivative of P0 to the 4. If it is equal to 0 almost everywhere, it means that P0 or U0 don't depend on the angular variables. So they are radially symmetric. Okay? So this is, I mean, I am skipping a lot of the proof. It's a quite technical proof because we need a lot of estimates around the origin at infinity to make the integration by parts and all that. So the most technical part of the proof is to prove the properties, the possible singularities and the k-properties of the solutions at infinity and near the origin. So it's very, very technical. But the general idea is that, so we have seen that by using this idea of nonlinear flows, or fast diffusion flows, we have been able to prove the optimal symmetry result for Caffarelli-Nirenberg inequalities. So no, I don't have time for that, but just telling you that we have explored the use of this flow also for other subcritical Caffarelli-Nirenberg inequalities, for other kind of inequalities, using the same kind of idea, the same kind of method, and every time we are able to prove optimal symmetry results. So we are really very happy with the result, because of course it was the proof of a conjecture, which was open for some time, but at the same time, probably happier than with the result, we are happy with the method, because we think we have found a very robust method of proving symmetry results in cases in which you can't use symmetrization techniques. But I am cheating, is my last word. I am cheating because we don't prove symmetry, actually. You think a little bit about our proof. We don't prove symmetry. What we prove is uniqueness of positive solutions. We prove that all the solutions have to be I mean, there is only one family up to some multiplication by constants and something like that. And since we have already the radial solution, but the only possible solutions are the radial solutions. So it's an indirect way of proving symmetry. It's actually what we really prove is symmetry. We prove rigidity, actually. Okay, so thank you very much.
Thank you very much for the nice talk. We have a few minutes for questions. Please, any questions? Are there any questions? Yes, please.
Sorry, I can't hear. Wait for it.
Would you expect these methods also to work in critical cases, for example, for the Galois inequality type, or for the Moser type inequalities where you have where the power is equal to the, for example, in the case where n is, the dimension is 2 and p is infinity?
We think that this method is going to work in many cases, not only critical but also subcritical, because we have been working also with some subcritical equations, and it works also. So we are very, very optimistic. The problem is that for every inequality you have to find the flow that goes with it, and there is no rule. We have been investigating different types of inequalities, and for every one we have to find the adequate flow. And in some cases you manage, in others you spend a long time trying to guess what the flow could be. But if you are lucky, you find the flow, you have a good chance of proving the optimal result for symmetry, yes.
Thank you. I think there's another question there.
Yes. Do you have an idea if your flow methods can give you information about the minima in the red region, when the minima are not symmetric?
Not really. I mean, we know things because there is a result of Willem and collaborators that prove that even when you are not symmetric, you are positive, you depend only on two variables. So in polar coordinates, you depend on the radius and one of the angles, the azimuthal angle. So they depend on two variables. So and you have an idea of the landscape of the function, and we have computed them numerically in great detail, and we see how they are, but we don't know how to compute them explicitly. But since it's only two variables, it's very easy to compute them numerically.
Thank you. Are there any other questions? No. So let's thank Professor Esteban again.